Hello, everybody. I hope you guys are doing okay. Tonight we're nearing the end of what is easily the strangest semester I have ever experienced in 37 years of teaching. We've had weather issues, we've had problems with the TV system at the college, but I don't think back in January any of us could have imagined that we would spend half the semester doing everything in this class online. The good news is you guys have actually done pretty well with it. And the better news is that we're almost done. In fact, tonight is the last night you actually have to learn anything because next week all that's up is test 4 and finishing up your project. This is actually the first of 4 videos of notes that you're going to have tonight. And I know that sounds like a lot, but I'm going to try and keep things moving as quickly as I can. There is one thing that is truly new. There are 2 that sort of sum up everything that we've done. And the last one deals with a review for the final test that you'll be working with. So we're going to talk about non-parametric statistics. Which test should I use? What do you do when? What else is there? And then the review for test 4. So the first thing that we're going to talk about this evening is non-parametric statistics, which is the very last chapter in your book. Non-parametric statistics are the fastest growing branch of statistics. And in fact, if you take almost any business course that goes beyond this one, you're likely to encounter some form of non-parametric statistics. The term non-parametric comes from the fact that statistics that are non-parametric don't use any parameters. They don't have any of the information about the population, things like those Greek variables that you had to enter into your calculator. Basically, with non-parametric statistics, you look at your sample and you count. That's pretty much all that's involved. There's some advantages and some disadvantages to non-parametric statistics, and we're going to take a quick look at what those might be. One of the advantages is that they require very little advanced information. Like I say, you're basically going to count. It's almost like you go back to that book, Everything I Needed to Know I Learned in Kindergarten, and go from there. Non-parametric statistics will also give you a quick and easy answer for what you need. You don't have to do complex calculations. You're going to have an answer of whether things are significant right away. So from your point of view doing non-parametric statistics, the advantage to them is they're easy. What statisticians will tell you is the advantage to non-parametric statistics, though, is that they don't make any special assumptions. They don't assume that you're working with a normal distribution, which almost everything else we've done in statistics does under the surface. And if you don't have a normal distribution, things like z and t-tests can go wrong really easily. Non-parametric statistics, though, they work if you have skewed distributions, if you have uniform distributions, if there's gaps, no problem. Unlike a lot of other statistics, non-parametric statistics are not affected in the least by outliers. You can have all the outliers you want and it's not going to change your outcome. So the advantage is, again, quick and easy. They aren't affected by outliers and they don't make any special assumptions about the population. Everything in stats has trade-offs, though. And the big trade-off with non-parametric statistics is they're not as precise as the traditional statistical tests you use. In particular, you're not going to get a number. You're not going to get like a p-value that you can use, or you're not going to end up getting a specific number for t or z or r that you can compare with other things. You'll get an answer yes or no, but basically that's it. Also, interpreting the test is a little bit different from what you've done before, although honestly, it's still pretty straightforward. There are tons of different non-parametric tests. Your book covers about 4 of them, and if I wanted to, I could look at about half a dozen others. But we're going to focus in on 2 non-parametric tests, basically just to give you the idea of how things work. The first of the tests we're going to look at is called the sign test. And a sign test is really versatile because you can use it for absolutely anything that you could divide into 2 groups. And there are tons of things that you could possibly divide up into 2 groups. Originally, sign tests were developed to answer the question whether there were significantly more things above a certain number than below it. In particular, what they did is they compared the median of a sample with what they'd expect that median should be. But you can go way beyond numbers and above and below. You can also look at whether things went up or down over time. I could, for instance, look at the stock market lately and say, have there been significantly more stocks falling than rising? Which I'm pretty sure the answer is yes. You can also look at absolutely anything that you could divide up into 2 groups and ask, are there significantly more of one than the other? Are there significantly more men in a group than women, for instance? That's the idea of what you can do with a sign test. I'm not going to ask you to write hypotheses for a sign test, but all they would be, the alternative hypothesis would just say there are significantly more in one group than another. The null hypothesis would say, no, there might be a little bit more, but basically those groups have roughly the same number. There are actually a whole bunch of ways that you can do sign tests, and we're going to do things a little bit differently than this topic is presented in your book. Your book takes a sign test and it basically, in a roundabout way, turns it into a z-test, which is taking something easy and making it hard, and there is absolutely no reason to do that. That's why in Canvas I have posted a table, and we're going to use that table to do our sign tests, because then it's exactly what I said at the beginning, you just count. What I'm going to do to find a value to compare is I look in that table and I look up the total number in my group excluding any ties. Now, when we go through some examples, that'll make a little bit more sense. But I have to have things that are either definitely in one group or definitely in the other. They can't be on the border. That's the n that I'll use in the table. You'll have some values of alpha that are across the top of that table. You go down and you find a critical value, a number we're going to compare. To figure out what we compare to that, I count up the number in each of the groups. And again, I ignore anything that's tied or equal to a test value. The test statistic is always just the smaller group. So like if I had 5 girls and 7 boys, 5 would be my smaller group. That's my test statistic. Whatever one's smaller, that's what you go with. Now, sometimes people ask the question, what if they're the same? Well, if they're the same, just use whatever number that is. Like if I had 6 boys and 6 girls, I'd use 6. But remember, the question we're trying to answer is, are there significantly more in one group than the other? And if it's the same, pretty obviously that's a no. There's not significantly more in one group than the other. Now again, everything will kind of make more sense when I go through examples, but the way I'm going to figure out for sure whether we have a significant result or not is I look at that smaller group, and it needs to be less than the number I looked up in the table. Kind of like your p-value always had to be less, for a sign test, you want the number in the small group to be less than what it is in the table. So we're going to look at a couple of examples here. The first one, it says Mr. Green thinks it takes less than 10 minutes to get to work. He recorded how long it took him to drive to work each day, and we've got some results. So you can see a bunch of numbers here, and if you look at those numbers, some of them are below 10 minutes, some of them happen to be above 10 minutes, And a couple of them are actually exactly 10 minutes. And the first thing I would want to do is count up how many things I have in each of those positions. How many of them are small, how many of them are big, and how many of them are just right at 10 minutes. So you count up all of those groups. Now the question we're going to answer is, did Mr. Green get to work in under 10 minutes significantly more often than in over 10 minutes? And it does say use alpha equals 10%. And again, the idea of what we're going to be looking at, if we have a significant result, then there would be significantly more that are in that less than 10 minutes group. If I don't get a significant result, we'd basically say that it was about the same number in the two groups. So here's those numbers again. And you'll notice that I have actually tried to highlight these a little bit. I put the ones that were less than 10 minutes in italics, and I bold-faced and underlined the ones that were more than 10 minutes, and I actually sort of crossed off the ones that were exactly 10 minutes. That's because I need to figure out how many are in each of those groups and go from there. So we got to actually separate them into the groups. If I'm doing a problem like this in a book or on a piece of paper, what I usually do is I'll get out a highlighter and just go along and figure out which ones are in each of the two groups. Now altogether, Mr. Green kept track of his times on 18 different days, but 2 of those days, it took him exactly 10 minutes to get to work. Anything that's the number in question, you always just throw out. So I don't use those 10-minute days at all. I just look at the ones that were more or less, and that's 16. So I'm going to use 16 for my n in this problem. So now I've got to haul out that sign test table. And I go down to the row where it says n equals 16. And then I go across until I find the column where it says 0.10 for alpha, and that's because it said use 10% back at the beginning of the problem. And it does turn out that our critical value is 5. So now I've got to figure out how many times it was below and how many times it was above and compare those two numbers. It does turn out on this one that there were 11 days when he took less than 10 minutes to get to work, 5 days when he took more than 10 minutes, and again, we totally ignore the ones that were exactly equal to 10 minutes. So my test statistic is going to be the smaller of those numbers, which is 5. When we do our interpretation, generally we want that smaller group to be less than the critical value. Now, I didn't say it specifically before, but it really is less than or equal to. If it's equal, that's okay. This time the number in our smaller group was 5, the critical value in the table was 5, and since 5 is less than or equal to 5, then yes, this is a significant result. So here's another example. It says, do people's scores go up if they retake the ACT? The following table gives people's scores the first and second time they took the ACT, and it tells us we're going to use alpha equals 0.05. So here's a table, and I know that you really can't read that word squat on anything, but what I would do with this is look at all the combinations of first and second, and like the very first entry, somebody got 19 the first time they took the ACT. They got 21 the second time, so their score went up. On the other hand, somebody else went from a 28 to a 27. Their score went down. I'm going to figure out how many of them went up, how many of them went down, and how many stayed the same. And it turns out on this one that there were 14 times that the score went up the second time they took it. There were 3 times that it went down, and there were 4 times that it stayed the same. So just looking at those numbers, yeah, it looks like it went up more often than it went down. Now the problem gave us information on 21 people who retook the ACT, but 4 of those, they stayed the same. They didn't go up or down, so I totally ignore those and throw them out. And all I care about are the others. There's 17 of those, so n is 17. I go to the table, I find the row that says 17, I go over to 0.05, and my critical value is going to be 4. What I always use to compare is the smaller number in my sample, and that would be the 3 that went down, so that's my lower number. And this time that number truly is less than the table, so yes, we definitely do have a significant result. Now, in my experience, people's scores do tend to go up when they retake the ACT. The problem is they usually don't go up enough. They usually are trying to retake it so that they can get a score that's good enough for either an admission or a scholarship. And a lot of times it goes up a point or two, but not enough for that. Here's another example, and it actually is based on a couple of lawsuits that did happen in the states that you can see at the side of the map. It says the Department of Chemistry at Big Time State University is being sued for gender discrimination. The plaintiffs noted that among last year's graduating chemistry majors, there were 50 men and only 34 women. The lawyer for Big Time State said there was not a significant difference in the number of male and female chemistry majors. And it says we're supposed to do a sign test at the .02 level of significance to see who's right. And again, the numbers they gave us were 50 men and 34 women. That means I got a total of 84, and none of them appears to be both at once, so I use all 84 of those. I go to the second page of my table, I look up 84 and .02, and my critical value is going to be 32. The smaller group this time was the women. It had 34 in it, so my test statistic is 34. And this time 34 isn't less than 32. And so this is not going to be a significant result. There certainly were fewer female chemistry majors in this class, but that could easily have just been due to chance. It doesn't say that there was necessarily a systematic problem that was causing this. And this actually is exactly the result that both Ohio State and the University of California ended up getting when they were actually in similar lawsuits. Now, you may have noticed that the table that I had goes up to 100. And a question people sometimes will have is, what do you do if you happen to have more than 100? Darn good question, and there's all kinds of answers you could have to that. One possibility is to get a bigger table, and there are tables that go up to all kinds of possible numbers. Another possibility is to do what your book does and take a sign test and convert it into a z-test. That's really just taking something easy and making it hard, though, and there is another possibility. The easiest possible way to do it is to take your numbers and convert them into percentages. Percentages will always add up to 100, and since the table goes to 100, that means they'll always work. So here's a quick example where we'll do exactly that. It says a software manufacturer conducted a poll to see what type of computer people preferred. They found that 237 people preferred Windows machines. 80 people preferred Apple machines, and 74 had no preference. Now again, those no preference people we're not even going to think about, because if they couldn't make a decision, we don't care for a sign test. The question is, did significantly more people prefer Windows than Apple? And again, I totally ignore the people that didn't have a preference. I just add up Windows plus Apple, and I get a total of 317. That's my total number of people that were in this sample. And now what I'm going to do is use that to figure out the percent of people that preferred Windows and the percent that preferred Apple. And I do that just by taking the numbers and dividing by 317. So basically 75% preferred Windows, 25 preferred Apple, and those are the numbers we're going to use for this test. This time we'll go to the very last row on the second page of that table, and I want 100 for my n, 75 plus 25, 0.01, which is that first column, and it turns out that my critical value is going to be 36. The test statistic is the smaller group, that's the 25, and it's smaller than 36, so yes, this is a significant result. And that brings us to the second non-parametric test, which has a rather unfortunate name. It's called the runs test, and whenever I hear the name runs test, it always makes me think that I've got diarrhea or something and I need to go to the doctor. But runs test doesn't have anything to do with having the runs. Instead, it deals with randomness. The question you're answering when you do a runs test is your data random? Or if it's not random, is there such a pronounced pattern that we should be suspicious of it and maybe make some changes? Runs test, you always want to know, is it random? Now technically, if I have a significant result, it means I don't have random data. Basically, a significant result means there's a problem and we need to make some changes. The null hypothesis would be everything's okay. It is random data, no big deal. And I also put in Canvas a runs test table. That table actually is in the back of your book also, but it's just sometimes easier for people to use it as a handout or online, and so that's why I put it there. That runs test table is set for the 5% level of significance, so that's what we're always going to use. You could do runs tests at other levels, but you'd need to get a different table to do it. Now what that table is going to give me is what we call a critical range. It's basically the numbers that would be good to be random, and they're not too big and they're not too small. The way I figure out what that critical range is going to be is, first of all, I divide up my group into two groups based on some obvious characteristic. This is kind of what I did with the sign test. I'm just going to count up the number in each of two different groups. And I'm going to use those numbers in the groups that I just counted and go to that runs table that's in Canvas. And what I do, you'll notice at the side it says value of n1 and at the top it says value of n2. That just means how many are in each of the two groups. I find where those rows and columns intersect, and that's going to give me two numbers that are the bottom and the top of this critical range. So for instance, suppose I had 9 in one group and 7 in the other. Okay, so I go to 9 at the left, 7 at the top, and where that row and column intersect, the numbers say 4 and 14. Now, we'll talk about what that means, but basically I'm going to find a number, and if it's between 4 and 14, we've got random data. If it's bigger than 14 or less than 4, we don't. Now, it doesn't matter which number you find at the top and which one you find at the side. I could have done 7 at the side and 9 at the top, and you notice I've got a square around another 4 and 14 because you get the same answer no matter which way you go. So I find those numbers in the table, and now I've got to have something that I can compare to it. And what I compare to it is what we call a number of runs of data. A run of data just means that I have a bunch of things in a row that all have the same characteristic. So you might, for instance, think about flipping a coin. If I got 3 heads in a row, that's one run of heads. If I then got 2 tails, that would be a run of tails. Maybe there's 1 head after that. That 1 head by itself is going to be another run of heads. Every time I switch, I change runs. So here's a similar example. And you can see I tried to make the heads and tails as different as I could with bold-facing, underlining, italics, and color to try and tell apart which ones are which. Again, what I want to look at is what goes in a row. So like heads, heads, heads at the beginning, that's one run. Then I've got 5 tails after that, that makes the second run. 1 head all by itself makes a third run. 1 tail all by itself makes a fourth run. I've got a head at the end of the row, and then I wrap over into the next row. And all of those three heads together are going to make the fifth run. The tail is a sixth run, the head is a seventh run, another tail is an eighth run. Two heads makes a ninth run, two tails makes a 10th run, and those two heads at the end make a total of 11 runs. Every time I switch, I have a new run, and I'm counting up how many of those do I have altogether. And I will tell you, when you've got problems like this, you always read across when you're going through situations like this. When I get to the interpretation, what I do is I compare that number of runs with those two numbers that I found in the table. And if the number of runs is somewhere in the range of those two numbers, it's going to be random data. So, like on an earlier slide, I had highlighted the numbers 4 and 14. I just did a problem with 11 runs. 11 is between 4 and 14, so if that went with this problem, yeah, this would be a random selection of heads and tails. It is okay if I got the borderline too. If I had gotten 4 or 14, it would still be, yes, it is random. If it's outside of that range, then it's not random. So like if I had gotten 16 runs, that would be like going heads, tails, alternating every time. That's not random. It also wouldn't be random if I'd gotten 2 runs, like a whole bunch of heads followed by a whole bunch of tails. Both of those are definite patterns where there's a problem. And again, it's got to be in that range that you're getting from the table. The question is always going to end up by asking you, is this random? So you just need to figure out if it is in that range, it's yes. If it's too big or too small, it's no. And I want to do an example that is based on an actual legal case that goes back to the 1960s and the Vietnam War. And if you actually look at the picture on the bottom right, you'll see what this one's going to be about. During the Vietnam War, the government did hold what was called a draft lottery to see who would be called to service first. Everybody's birth date was assigned a number, and those that were assigned number 1 were the first people to be drafted and ship off to Vietnam. The date that was number 2 was second. And then they'd keep going through the list until they had however many people they needed, and those people would go, the people with the other birth dates would not. They selected those numbers by putting balls into a bin and then drawing them out one at a time. Sometimes it was an employee of the Department of Defense that would draw out the balls. One year it was Richard Nixon, the president, that drew out those balls. So it varied, but they would have somebody reach into the bin, draw out what the first date was, what the second date was, and so forth. There was a very famous lawsuit that asserted that those draft numbers were not randomly assigned. And what they actually said in this lawsuit was that people that were born in the last half of the year were more likely to receive low draft numbers, and thus they'd have to go off to Vietnam. I actually had 2 brothers that were of draft age when the Vietnam War was on. One of them was born in November and one of them was born in August, and you can imagine that they might have actually cared about this lawsuit. Now I'm going to tell you, to model this, I have some things that I have totally made up, but it gives you the idea of how this worked and also what the final outcome of the case was. I have here, suppose the first few dates selected were as follows. And you can see I've got a bunch of dates there. Now, again, I totally made these up. These are not the correct dates from any particular year, but you might notice something about every one of these dates, which is that they're all in the second half of the year. And here's a few more that are also mostly in the second half of the year until you get the last 3 in this list that happen to be in the first half. Now again, I completely made up those numbers, and in the real situation, they weren't quite as obvious of a pattern as what I came up with there, But with 365 days, you don't have to have as big of a pattern to come up with a significant result. Here, I had 17 dates that were in the second half of the year, 3 dates that were in the first half, and there were 2 runs. There were the first 17, and then there were the other 3. And of course, what I've got to do is find that critical range. I go to that table. My larger number is going to be 17, my smaller number is 3. And here I went to 17 at the top and 3 at the side. Again, you could do it the other way around and you'll get the same answer. My critical range here is going to be from 3 to 8. If I have between 3 and 8 runs, we would have random data. Otherwise, we don't. I already told you that we had 2 runs here. We had 17 days that were in the second half of the year, followed by 3 that were in the first half of the year. So it was a total of the 2 runs. And 2 is definitely not between 3 and 8, so this would not be random data. And while I did just make up the dates I had there, it does give you exactly what the actual outcome of the case was too. They looked at the entire year and they did a somewhat more complicated analysis than this. What they ended up finding was that the balls that were in that bin hadn't been properly mixed. When they set them up, the person that put the balls in there put January on the bottom, and they kept adding balls to it until they got to December at the top. The people that were picking them, they might stir the balls around a little, but they rarely would go clear down to the bottom to grab a ball. So they actually fixed this the year after the lawsuit a couple of different ways. First of all, instead of having somebody pick the balls, they went to like the lottery is drawn on TV where they shot things out of a machine. And they also actually used 2 machines. They had a number that came out of one and a birth date that came out of the other, and they would just match those 2. And that did make the last couple of years of the Vietnam War, the draft lottery was a lot fairer, but it would be interesting to think how many people might have died because that lottery was unfair. We'll take a quick look at one other runs test problem. It says here are some numbers. We're supposed to use the characteristic of odd and even to decide if these are random. And here we've got some even numbers that, again, I've bold-faced and I have put in italics, and I've got some odd numbers that I underlined. You could count them up, and you could hopefully figure out what our number of runs is as well, looking at those. You might want to pause for just a second and try and figure that out before we go on. It does turn out in this one that there are 11 odd numbers and 9 even numbers. And if you go to your table and you use 11 and 9 at the side and top, the place where those intersect, the 2 numbers that are there are 6 and 16. That's our critical range. In this problem, there are 10 runs of data. And again, I start with the 4, that's the first run. I've got 7, 3, 5 for my second run, 2 and 6 make a third run, and then you continue from there, alternating now and then with the rest of them. But there are a total of 10 runs of data. And since 10 is between 6 and 16, then yes, we do have random data. And hopefully that makes some sense as to how sign test and runs tests work. You might want to take a look at the practice problems that I have online that you can get a little bit of an idea of how both of those do work. And of course, you will have to do those when you get to test 4. That's it for the first of the videos. Again, there are some others that you're going to want to look at this week as well.